Hello everyone. Today we are going to talk about a seldom seen vulnerability called precision issues that typically affects graphic libraries. So what is precision issue? The root cause of such issues is using limited precision arithmetic in cases where a precision error would invalidate security assumptions made by the application. What is the difference between integer overflows and the precision issues we are talking about here? For integer overflows, we are dealing with arithmetic operations. At a given precision, the magnitude of the result is too large to accurately represent. And for precision issues, we are dealing with arithmetic operations where the magnitude of the result or a part of the result is too small to be accurately represented in the given precision. These issues can occur when using floating point arithmetic in operations where the result is security sensitive. Let's look at some examples. So here is the first example. So what is the result of C here? Since float typically only allows for 24 bits of precision, the result is actually going to be 100 million here. If an application makes the normally reasonable assumption that A is greater than 0 and B is also greater than 0 implies that A plus B should be greater than A, then this could lead to issues. In this example, the difference between A and B is so significant that B completely vanishes in the result of the calculation. But precision errors also happen if the difference is smaller, for example. So what is the result of C here? As we can see, the output is smaller than the precise result. No matter the difference is big or small, precision errors will happen. Let's talk about the SwiftShader. SwiftShader is a high-performance CPU-based implementation of the open graphic libraries, embedded system, and direct 3D naïve graphics APIs. SwiftShader is used in Chrome on all platforms as a fallback rendering option to work around the limitations in graphics hardware or drivers, allowing universal use of web graphic libraries and other advanced JavaScript rendering APIs on a far wider range of devices. SwiftShader is quite an interesting attack surface in Chrome, since all of the rendering work is done in the GPU process. Since GPU is responsible for drawing to the screen, it needs to have more privileges than the highly sandboxed render processes that are usually handling web page content. So where will the vulnerability occur? Upscaling or drawing from a small cell's texture to a larger area. This requires computing memory index using non-integer values, which is where the vulnerability occurs. An information leak issue resulting from some precision issues in the SwiftShader code. So let's look some example code of SwiftShader. This piece of code is trying to copy the pixels from one screen to another. However, because of the precision issues we just mentioned in the above cases and examples, it could finally end up with out-of-bound error due to the floating point. And the highlight part is we will make some changes to reduce errors. And this is kind of a naive solution could reduce errors. If this approach had been used instead, actually we will still have precision errors, but without the iterative calculation, there will be no propagation of the error, and we could expect the eventual magnitude of the precision error to be stable. We are fairly sure that comparing to the implementation with iterative addition, the multiplicative implementation will be roughly correct. Here is the graph showing the difference between two algorithms and seeing where the results are most different. As we can see, up to 2046, the values are still identical, But at 2047, the first significant errors start to occur, and the incorrect answer is smaller than the more precise one. At 2857, the two computations coincide again, and we can see that the last index is sufficiently different that int conversion results in an out-of-bound index. The multiplicative algorithm would remain within bounds, but the iterative algorithm could not. Note that there will also be error in the safe calculation. It's just that the lack of error propagation means that error will remain directly proportional to the size of the input error, which we accept to be small.
So we talked about precision issues in SwiftShader, and it turns out that another commonly used library, which is called Skia, has similar issues. So Skia is an open source graphics library, and it is commonly used to draw HTML elements like canvas and SVG. As a graphics library, it will do bounds check for each object it is going to draw, and which is to say, it will make sure that an object will be drawn only if that object is inside the drawing area. And if you draw things outside that drawing area, it might cause out-of-bounds memory corruption. And you might think that Skia will do bounds check for each pixel, but bounds check are expensive in terms of CPU cycles, and Skia is fast, so that's not how Skia works. So the strategy Skia uses depends on the relative location between the object and that drawing area. So if the object is outside the drawing area, Skia will do nothing in return. And if the object is partially inside the drawing area, it will do bounds check for each pixel. And if the object is in the drawing area, Skia will draw the object directly without any bounds check. And the third case is where precision issues may cause vulnerabilities in softwares. In that case, the per pixel bound check is turned off. But the problem is that for each pixel you draw, there may be some rounding errors. And when you draw more and more pixels, these errors add up to very big. And the first vulnerability in Skia we will talk about is caused by integer to float conversion and multiplying fractions. So there's a function in Skia that converts float to the closest integer. And if the input is negative 0.499, since floating point cannot be exactly represented, that function somehow rounded to negative 0.5. And there's also precision issues with fraction multiplication, and the difference between the expected result and the actual result could be very significant. When these two errors are chained together somewhere in the code, it finally leads to an out-of-boundary error. If an attacker could somehow trigger an out-of-boundary error, they might be able to trigger a denial of service attack. So the next precision issue in Skia involves drawing the splines. You can simply think of spline as a curve, and to draw a curve, it will first be divided into small segments, and Skia draw the entire curve segment by segment. And the problem is that for each segment you draw, there's an error associated. And as you draw more and more segments, these errors add up and get snowballed to a big one. And in this HTML code, we're trying to draw a vertical line on the left of the browser. And because of the precision errors, as you can see in the picture, part of the line gets spilled to the other side. So the issues in Skia that we just mentioned are solved in a rather simple way. The developers of Skia simply increase the safety margin, namely, to make sure that the maximum rounding errors are within the safety bound, so that drawing an object is more likely to trigger per pixel bounds check, and that's gonna make the program safer. So that leads us to two questions: how to avoid precision issues and how to find them. So to avoid such issues, just try not to use floating point arithmetic. And if you really have to, make sure you have fully considered the worst scenarios. namely the maximum errors that floating point arithmetic could cause, so that they won't cause out-of-boundary errors. And in some cases, precision issues also exist in integer arithmetic. And in that case, you'll need to be extremely careful with operations that could reduce precision. So in terms of how to find such issues in an existing program, unfortunately, there are no good ways to deal with them. And in that case, you'll probably have to use some old school ways, like manual source review, fuzz test, which is to generate random inputs to make the program crash, or to brute force all the possible inputs. And that's all for our presentation. Thank you all for listening.